to kind of reflect on how we learn. So remember when you are at school as a child and somebody teaches you how to do addition. So the teacher comes and it's like, this is how you do addition. 3 plus 8, 11, carry, it's like, you put down 1 and carry the one other and then you do the addition. And
I'm going to clip my cue up just
okay.
quickly. There you go. And do you want to pop that?
Okay. Okay. So, and then, oops. And then you move, let's say, to university. And I still remember the first day at university where the teacher goes, it's like, 1, 2, 3, 4. Okay, natural number. Tell me what is a natural number. And it's from, we know the examples, we know what is a natural number, but then you want to know what are the rules to building a natural number. So it's like, okay, it's a set, and you define the 0, and then you do it by increment. And so, you start from somebody gives you the rule, and you run them on instances, then you have the example, and then you extract the rule, and then you move to a PhD or to work, and nobody gives you the example. Nobody gives you the rule. You have to find them by yourself. And that's where kind of collaboration comes into account, and how you put things together, how you interact with the rest of the world to build your own example and your own rule. So what I'm saying that, it's pretty much the same for software. So we start, and that's still the traditional way we write software. You write the program, you write the rules, and then you have your computer that execute the rule, give you the example. Increasingly, we're moving to an approach where you give a lot of examples, you give the desired outcome, and it's the role of the computer to write the program, to write the rules. Now, and that's the thing that's also closer to my heart, is through collaboration. So when you consider now, services, the web or Internet of Things, you have a lot of small devices, you have a lot of small software, and the magic is the emergent behavior is when these multiple things talk to each other, and the idea of putting them together is what makes the bigger behavior, what makes the bigger system or software. Okay, and today I'm gonna really focus on these 2 areas. So although the traditional software engineering, I think a lot of people know it already. So, and if we consider machine learning, you have this almost two ways of looking at it. You have this, oh, it's gonna make a huge economical, profit. It's gonna revolutionize the way we live, the way we write software. And then you have also the other view, which is, oh, everything is gonna break. We have no idea how it works. Everything is gonna be obfuscated, and actually, it's not all doom and gloom, and it's not this blue sky. So the idea, and that's, do you know who's this guy, Bennaceur? Yeah. So he's the guy who basically invented internet, so IP, and he works now at Google actually as an internet evangelist. But he's the guy he's a Turing Award laureate, and he's at the heart of IP protocol and the internet. So, and the idea is actually, yes, let's explore how machine learning works, but at the same time, let's kind of still build software that is reliable and that is resistant to abuse. Because by the end of it, whether you write software or you use machine learning, it's still software, and we need to build resilient, robust software. Okay, so then the idea of with the software engineering at defining the processes and the engineering methods to build software now. Because we need the same methods also for building quality software, and this is kind of challenges the traditional methods because it's usually long-lived, so it keeps learning, it keeps evolving as the system is being used. It also deals with interactions that are not necessarily foreseen. So you need to adapt to the environment. So what we need is we need methods to reason about the design and of resilient ML and to build them. Now, if we look at the way the two almost areas work, so in terms of software engineering, a lot of the methods is you try to plan your software, how it works. So you try to understand the problem to implement a solution. And there is a very important principle in software engineering, which is, the divide and conquer. So you have a big problem, you try to divide it into a smaller sub-problems and solve these sub-problems, then integrate, okay? So while machine learning is the other way around. You have a lot of data, so you have a system that is already running. And then the way it works is you implement a kind of a technique and then try to understand the problem and evolve it. And it's one of the strengths and one of the problems of the machine learning is you always look at the system as a whole. You don't break it down. You try to analyze the system is in entirety. So this also, so when you collect the data, it's about the system as a whole, rather than when you do the software where you kind of try to understand the behavior, how the sequences work, how the system work, okay? So if we, and that's one example, if you consider, for example, designing a car, let's say, or the system for a car, then you design specific subsystem. You design the entertainment system alone, you design the bus for the interaction alone, you design the braking system alone. While, for example, if you use machine learning as a perception environment within a self-driving car, then you consider the car as a whole. And you try to define, for example, what is a pedestrian, but without breaking, for example, a pedestrian is a head and the feet and everything. So you try to have the features of a pedestrian as a whole. Now, in terms of processes, and so this is the spiral process and kind of how you build, in terms of how you build software. So you do the requirements, you design, you implement, you test, and then you evolve, you revise your requirement. And then it's a kind of, it's a spiral process, so you keep iterating. And it's the same with Devops. Have you heard of Devops? Yeah, so it's also another way of developing software where you basically plan what your software does, you code, you build it, you test it, you release, and that's kind of this cycle where you have a lot of releases, each feature, and as you are releasing and building your system, the idea is to have this kind of sprint and deploy, and it improve your understanding of the system and how it works. So yes, so you plan, you release some features, you deploy it, you monitor how it works, and then you plan again, and gradually the software is evolve and include more features and is better accommodated. So in terms of the machine learning workflow, you still have to define your requirement. What does my system as a whole do? And then you collect the data, you clean it, you label it depending on the algorithm you use, and then you do the feature engineering, the model training. You evaluate. You may also come back to train the model again or to relabel the data, and then you deploy it, you monitor it. So, and that's okay, so this is a kind of defined in the by Microsoft actually research, this kind of workflow, but it summarizes the way a lot of projects work, a lot of machine learning projects work. So a kind of, that's a question for you because we're a small number of people, so we can interact. What's the common kind of big step between the two? Between the first, those ones, so those ones where you do the requirement, you design, you implement, you test, and here, where you do the requirement, you collect the data, you train the model, and then you monitor it or you deploy it. Yeah, thank you. So even though the way you approach problems are different, the main kind of things that put them together is this requirement. So whether you build a system by specifying each step or you learn the behavior, a big part of it is in terms of requirement. So in terms of the software engineering, the requirements are actually sit between the problem space and the solution space. So in the problem space, we try to understand our problem. In the solution space, we're building the software to solve our problem. So the requirement will help us kind of define the feasibility of the system, but also kind of define our design choices, drive the implementation so that, you know, the implementation satisfy what we really want, so those requirements. And then we can also test the running system. So the requirements are a set of properties that the system need to have and that the stakeholders want the system to have. So the stakeholder can be customers, can be users, and they want certain properties of your software. So usually the requirement engineering process have four steps or four main activities. The first one is elicitation. So every stakeholder have an idea of what they want to see in the system. So it's elicitation because you want to kind of understand what they want and also understand the domain, the assumption, so that you write them down, you specify them. The second step is you want to model them because is basically going from the stakeholders, from your users, your customers, into a way that an engineer or somebody who implements the system will understand. And then the third step is what we call assurance. So you want to validate that what you specify is the right thing that the stakeholder wants. And the fourth activity is actually going back and seeing, you know, deploying and testing and learning and evolving. Okay? So I'm going to go into each of those activities. So elicitation, we have two things. So we have what we call user requirement, but really it's just all stakeholder. It can be the customers, it can be you know, the owner of the product, it can be another kind of user of the product, anyone. And that basically is the desirable properties of your software. The other type is the system requirement, which is the desired properties of your system, or here often of your software, so that, you know, your software satisfies your user requirements. So an example is what does the software need to have in order for the user to be satisfied. So an example is if you say, you know, you're designing a system of ticketing, and then so accessing to a platform, into a train, for example, and then you say, you know, the passengers present the ticket to the reader, and you're designing, for example, the reader, and it's like, you know, the passenger accesses the platform when the door opens. So you have also domain properties on that. Okay. So and the main idea between the difference between the two is you want to create what we call a satisfaction argument. So a satisfaction argument is you have domain properties, and that's your assumption. And then you want, so that's actually the fundamental law of requirement, where you have under certain assumption, and assuming that the software really does what we want it to do, then you will satisfy your stakeholders or your customers. And this way, you can have multiple assumption and multiple system specification. So, for example, you want people to cross the road safely. So there are different ways. You can define, for example, zebra crossing. You can define traffic light. You can have a policeman. There are a lot of ways of doing it. So, but if you say, there is a zebra crossing and that's your specification, then you're assuming also that, the drivers will stop at the zebra crossing. So that's actually your domain assumption, because you can't control that if you are a designer of the zebra crossing. But that's actually to make people cross the road safely. Then you can build a zebra crossing, but it's not under your control. So that's for somebody else, from the law or for something else. Okay. So, and that's the idea of the requirement. You go from a high-level objective, and you try to specify the assumptions and break it down into what we call agents. So what the system needs to do, what the people need to do, and kind of assign differences. Now, there are different, more kind of structured ways of doing it. So that's, for example, chaos. You don't need to understand everything, but it's basically working with refinement. So you have a high-level requirement, and then you split it into smaller objectives until you reach here, and then you assign it to someone who does it. Now, the main idea is you need to validate that. So you have your specification of what your software does, and the validation is about comparing it to stakeholders, so making sure that the customers really want these properties. And once you deploy the software, is verifying it against it. And for that, there is always a kind of formal techniques to ensure that this is the case. Now, one of the problems is all that is yes or no. So a lot of these techniques that we have in software engineering is either yes, you satisfy the property, or no, you don't satisfy it. And there isn't a lot of, and that's what's maybe needed for a lot of new software in machine learning, is that the ability not to be no failure, but actually the ability to be resilient, to come back to a stable state. So rather than satisfaction, you need what we call equilibrium or resilience. So the ability to go back to that. And one way to do it is the need for human expert or insight, because this is what you need for selecting the data, for making the trade-off, and for evaluating the results or verification. Okay? And to kind of also put it in context, I'm going to present two cases where we use both of them. The first case is in terms of interoperability, so making systems talk to each other. And the second one is a socio-technical resilience, and I'm going to talk about each. So first, the interoperability. So the main objective here is, if you consider, say, a simple application, file sharing. There are a lot of applications. So I know it's a kind of supported by Google. So we have Google Drive, for example, but we can use also Dropbox. And this is, for example, WebDAV, and that's actually the standard for file sharing. And they all, at a certain level of abstraction, they all do the same thing. They allow you to read file, to share file, to write files, right? Now they do it differently. Each one has different interfaces. So the way they define file, the actions, the name of the action, some say, download, the other is read, for example. Some say upload, the other would say, write, for example. And that's so you have different actions which at a certain level of abstraction, they do the same thing. You have also what we call different behavior. So the behavior is basically in which order you can execute the actions. Do you have to list all the files before kind of writing or not? Do you have to lock the file before accessing it? So they have different behavior. And they are also implemented differently. So here, for example, they will encode using JSON, which is a markup language. Others will use XML. Some use HTTP. The other use SOAP, for example. So they have different protocols to implement them. Now, and that's the middleware solution. So middleware is just standard protocol, standard platform to develop those kind of communication or connected application. Now the issue is when you move, then they are not able to interact. So WebDAV, for example, those who use Mac, Finder will support this standard. But if you want to access a Google file, then you can't, a Google Drive file, then you cannot use your Finder. You have to install a new application. So the idea is, can we just put them together? Or do we need to install all applications? So that's the interoperability bit. So there are different ways of doing it. So if you consider the normal way, and I'm kind of doing the mapping between protocols and languages, basically. So if each machine speaks a different language, the idea is, well, to define a standard. So, and think of it like Esperanto, for example. That's the standard, the thing that covers all the protocols. And for different applications, sometimes it works. For example, for the email, you use SMTP, and it worked. For file sharing, they defined a standard, WebDAV, that nobody is really interested in. Well, not nobody, but that's not still kind of a lot of people don't know even that it exists. And it's the same for instant messenger. There is a standard protocol called XMPP, but Google uses it underneath, but changed it as well. But there is a lot of instant messenger. So sometimes there is no, it's not a technical problem necessarily, but there are other problems that stop people from kind of following the same standard. The other way is, so there is no one fits all. This other thing is to choose one language and then have adapters to it. So think of it as English, and then you have translator to everything as English, and then from there, Now, one of the things is sometimes you have loss once you kind of have this common abstraction. So it doesn't always work. So for this abstraction, because this abstraction is supposed to include everything, which is often not possible. So, and that's actually, in terms of protocol, is called like enterprise service buses. And this is what they do. They do kind of try to define a common abstraction. The second thing is what we try to generate it on the fly. And that's what we call like almost having a Babel fish. So Hitchhiker's Guide to the Galaxy fan? Yeah. So what you try to do is really to have this kind of Babel fish. Now, creating something like that for the software kind of require us to observe, to synthesize, to deploy this kind of translator on the fly. So what we did is like, okay, we can't directly create this translation. So what we do is we try to abstract. We try to put them in a format that we can reason about. And that format is what we call a model. And the way we do this model extraction is through machine learning. So to understand what is read, then you use, for example, categorization functions to extract it. To understand the behavior, the models, we use a kind of special machine learning technique called L-star, where I think the easiest way of looking at it is almost active learning. So you press all the buttons until you realize how you should interact with the software. But then you have the translation. So between, for say, upload and read or download and write. No, the contrary. And then you do what we call controller synthesis. So you try to work out what is the flow that you need to interact with in order to ensure that you interact with your software correctly. And then the last bit is you want to go back down, because by the end of it, you need to generate software. So you need to put back the protocols, okay? So the idea is, well, does it work? Yeah, well, we can do it for many kind of applications, something like instant messenger, file management, event management, or like in rescue. Now it has some difficulties. So I'm going to play a small video, and I'll show you the thing. So in this one, we have devices in your home. So that's me 6 years ago. So say I forgot my phone here, and I have 2 robots, for example, that will collaborate to hide it. Oops, I sped it up, so you lost it. So the robot tried to call me. I don't come back. So they will try to work together so that my phone is not stolen. And that's their requirement. The requirement is to protect the phone from theft. It's sped up and kind of treated, and you will understand why. So it's very slow. So you have that, and then once they give it to that, they will put it in a safe place so nobody steal it. So that's the idea. So you have 2 robots, each one created by separate, different manufacturer, but what we want them is to create this kind of magical software that put them together. Now, does it always work like that? Actually, no, you have this. And that's one of the things, is once you try to reason correctly, things go wrong. And you have to deal with these things when, you know, when things go wrong. Yeah?
In the future,
yeah.
The real potential is we'll have all of these machines and these robots doing various things, but they'll have some mechanism whereby they can communicate, even though if that wasn't designed in at the original specifications.
Yes, exactly.
They'll learn how to communicate with each other.
Exactly, exactly. So part of that is learned, part of it is also kind of, you try to engineer it so that it fails the least possible. But you can still expect it to fail from time to time. Yeah. So yeah, so the idea is actually not only make them talk. One is to, because there is this risk of failure. Yes, you can learn, you can do the synthesis, but then when you deploy it, you execute, then you may also fail. So you have to learn from this failure and refine this communication as you go along. And that was the idea, is this notion of evolution and of always assessing so that you learn better and you make them more robust as they evolve and as they are deployed. So, and that's the, yeah?
I think it was just a kind of, this is a bit general, but
yes.
In sort of the software engineering, it's like you want to do something, so you explicitly program for that end result. So it's like, I want to do this, so it's coded for that. Whereas in machine learning, there's more of that unpredictability of, because you're just doing on the data analysis, that what you'll get out isn't actually what you intended. So then when you're coming to the testing part of it, I was just wondering, is there more scope for unpredictability or compared to traditional software engineering, or do you think actually you can negate it and do things like saying any other outcomes do not, execute, or think, how do they count for that?
Yes, so there is so one, what we call like, is almost deductive learning, where you go from the general and then you go to a specific thing, and the other, when you do a kind of inductive, so you have some experiences and you generalize. Once you generalize, there is a scope for failure, yes. Yeah. So there is this unpredictability. Now, one thing is to, to recognize that there is this possibility of failure and try to somehow control it or learn from it, so that, yes, it can fail, but it doesn't fail, it doesn't have the same failure twice. So
I think for me it wasn't necessarily failure, it was more that evolution is unpredictable, potentially.
yes,
So
yes.
the unintended consequences, I think it was that aspect.
Yeah. So for the unintended consequences, that's why you use kind of almost behavior analysis. So you try to almost kind of simulate it somehow. To kind of, you have your model, which is your abstraction, how it works. So before you deploy, you play it on the model.
Yeah, so it's the same kind of testing that you would do.
Yes. Okay. And then kind of see how it works. But then when you see, okay, I actually was predicting that it wouldn't fail, but it failed. So you kind of compare the two and try to make your model evolve so it reflects the real behavior. So the next time you analyze, it's actually more accurate and better. So that's the idea. Does it make sense?
Yeah.
Okay. So the second bit, and that's so the second case, and that's still an ongoing kind of work. And so far it was really kind of focused only on only on software. There's no people in there. So we're trying to include kind of a lot of how do the system interact with people as well. So we have this a project which is called, Stretch, and it supports healthcare. And the idea is you have, for example, an older person, and they have a circle of support. So you have their neighbors, their family, their community, everyone kind of helping them stay independent and at home for a long time. So the way we do it is, So the way we do it is to have still a big requirement, for example, is like minimizing social isolation, and then trying to see from the devices that are already deployed at their home. So they are actually instrumented, the homes are instrumented. So for example, at what time they go to sleep, whether they shower. So you build a kind of almost a pattern of their behavior. So one thing that you notice is people who are kind of suffering from social isolation, their pattern of behavior kind of degrade or change gradually. So the idea is actually to be able to do the analysis of the behavior and try to detect deviation from this behavior. And according to that, you do what we call intervention. Intervention can be as easy as, kind of calling a friend or calling someone to visit them, but then see how it acts on their kind of social circle of support. So you do also the intervention, and then you review and you monitor. So it's just kind of increasing almost increasing the uncertainty, because that we don't know how people react to this kind of intervention. So you learn from, each time I ask a friend to do something, then they feel better. So you need so we have devices, for example, to help them kind of assess their mood, and then we can also send them you should go for a walk or do yoga, and then see how that affects their mood, and then gradually build an understanding of how we intervene. So that's this end is still on working. So that's the main idea, where you actually, because there are areas where we don't have perfect understanding, so it's kind of deploying, and as our system learn, our actually understanding also kind of evolve. So to sum up, and that's the last slide. The one before last. So the idea is always we have some understanding of our domain, and that's the software engineering part. But there is so much uncertainty, so much areas that we don't know, that you have actually to kind of deploy and have the data drive your understanding and make your knowledge get bigger. but that also involves a way of tolerating this uncertainty. Okay, so, but to finish also on a positive thing, is still kind of a lot of theory needed to understand, you know, these assurances, this ecosystem. We need also part of engineering to deal with the human insight, to deal with this decentralization and uncertainty. We need more exemplar. I think I put also in the theory in terms of education, because if you do kind of software engineering studies, then you're taught certain way of writing software, of developing it, but a lot of the machine learning is actually contrast with the way we solve methods. So having an education that includes both is also important. So that's actually the 3 takeaway from, you know, making these two areas talk to each other. So thank you. I hope you enjoyed it. And I'm ready to take more questions. Do you have more questions?